All right, so this problem is going to focus on a word problem and application problem dealing with dealing with rational expressions. Specifically, one of those distance formulas here where you might be going upstream or against the current, or maybe one of the other possibilities is talking about a plane flying into the wind or against the wind or that kind of thing. So first off, let's go ahead and let's read through this problem so we can see what we're talking about here, and then we'll discuss how we solve this thing. So in this specific example, we're talking about Kevin, and Kevin has a boat that is traveling at 35 miles per hour. What it's asking here is it says to find the rate of the river current if she, I think that's supposed to be a he, Kevin is a boy, right? So if he can travel 6 miles upstream in the same time that he can go 8 miles downstream. So he's in a boat, he's going about 35 miles per hour, and it's talking about, well, find the rate of the river current. So how strong is the current of the river if he can go 6 miles upstream in the same amount of time that he can go 8 miles downstream? Now, to start off with this problem, the first thing that we definitely need here is we need the distance formula. Distance is equal to rate times time. And what we're going to do is we're going to create two different distance formulas so that we can take these two formulas and set them equal to each other and solve that. Now, the way that that's going to work here, so we have distance is equal to rate times time. So let's take into consideration our first scenario. So our first scenario is going to be going upstream. So if we're talking about going upstream first, so it says that he can travel 6 miles upstream. So 6 miles is our distance. So I'm going to say 6 is the distance, and that's going to equal 2. Now, another big component, another big part of this problem here is that the rate that we're talking about here is going to be different whether we're going upstream or whether we're going downstream. Because think about it, if we're going upstream, we're fighting the current. It's going to be harder for us to travel upstream against the current than it's going to be going downstream. So what we do with that situation here is we take our rate, we're going 35 miles an hour, but we're going to subtract an X amount, and that's going to represent the current of the river. So 35 miles an hour minus X because we're pushing against it. And that's going to be our rate. And then our time is just going to be T. We don't know what time frame we're talking about here. So it just says that we can do 6 miles upstream in the same time that we can do it downstream. So let's see if we can focus on the other equation. So when we're going downstream, we're flowing with the current. So it says that we travel 8 miles, right? So I'm going to say 8 is the distance, and that's going to equal to our rate. Now, our rate is 35 miles an hour, but here we're going with the current, so we're going to be going a little bit faster. So instead of having a minus X, we're going to have a plus X. Okay, and then we're also just going to say that T is our time. Now, these are our two equations that we're going to be dealing with. Now, what we're going to do in order to solve this thing. So remember that it does say that the time is going to be the same for them. So this time is the same thing as this time here. So what we can actually do mathematically is we can set those times equal to each other. So what we're going to want to do before we even do that is we're going to want to take each one of these equations and we're going to want to solve them for T. Because if we can get them solved for T, then we can set them equal to each other. We can solve this thing. So what I'm going to do is I want to move these off to the side a little bit here. So I have 6 is equal to 35 minus XT. All right, and then I also have, so 8 is equal to 35 plus XT. And what I'm going to do is I'm going to work on solving each one of these for T. So if I want to get T by itself, that means I want to get rid of this 35 minus X. And since it's being multiplied, what I'm going to do is I'm going to divide it to both sides. So 35 minus x cancels with 35 minus x, and I'm left with t is equal to 6 over 35 minus x. And do the same thing with the second equation. We want to get this one also solved for t, so we want to get rid of the 35 plus x, and since it's getting multiplied, we do the opposite and we divide. It's going to cancel on the right hand side, and t is equal to 8 over 35 plus x. So it's very, very important that we use the distance formula. So distance is equal to rate times time, and that we understand how to plug into the distance formula, specifically going upstream or downstream. Again, if you're going with the current, that's a plus x. Against the current, that's a minus x tacked onto that rate. So now that I have them both solved for t, essentially what we're doing is almost like a substitution. If t equals 6 over 35 minus x, what I can do is I can take this and plug it in for this t over here. So what that's going to look like is I could have 8 over 35 plus x, but instead of equaling this t here, I'm going to have it equal to 6 over 35 minus x, because that also equals t. So essentially we're just setting them both equal to each other. And what we're going to do is we're going to solve this thing here. Now, in order to solve this thing here, so unfortunately here we are dealing with rational expressions. There are a couple ways that you could go about solving this here. The first way that you could go about solving this is that you could get common denominators, and you can multiply the entire equation by the common denominator. This is going to help you get rid of your fractions, and it's going to help you be able to solve this problem that much easier. The way that I'm going to solve this problem here, when I look at this problem, I see a proportion. Right? So I see a proportion, two fractions that are equal to each other. So what I'm actually going to do is I'm going to cross multiply and solve this thing. I'm going to say 8 times 35 minus x, so 8 times 35 minus x is equal to 6 times 35 plus x. So I'm going to use cross multiplication to solve this proportion here. Either method is perfectly fine. You can find common denominators and multiply the whole equation by that common denominator. Or you can notice that this is set up the same way a proportion is, cross multiply. So I'm going to go with that method here. So if I cross multiply, 8 times 35 minus x is equal to 6 times 35 plus x. Let's simplify this thing so we can solve it. So the first thing I'm going to have to do is I'm going to have to distribute both sides of this. 8 times 35, so let's see, 8 times 5 is 40, 8 times 3 is 24, so that's 280. Minus 8 times x is 8x. And this is going to equal to 6 times 35, so let's see, 210 plus 6x. We're going to need to work on getting x on one side, our number on the other side. So I'm going to add 8x to both sides here. Negative 8x plus 8x will cancel, leaving me with 280 is equal to, drop down the 210, and 6x plus 8x is 14x. Since I have x all by itself on the right hand side, I'm going to subtract my number to both sides, leaving me with 14x is equal to 70. Last step here, we have 14 times x, so the only thing left to do here is to divide out the coefficient, and 70 divided by 14 is 5. So I'm left with x is equal to 5 here. So going back up here, so find the rate of the river current. So the river current, that means, remember, x represents the river current. So 35 miles an hour minus 5 miles an hour when we're going upstream, or 35 miles an hour plus 5 miles an hour, so 45 miles if we're going downstream with the current. So otherwise, 5 miles per hour is the current of the river here. So there's a lot of different components to this problem here, especially that distance formula, understanding how current works and how that's going to be incorporated into our problem, and then of course the math involved in being able to solve this thing.